So, hello everyone. Myself, Dinesh Kumar, and my expertise is in aircraft structures. So, in this session, we'll be discussing some basic concepts of aircraft structures, and these concepts are going to be helpful for you guys once like classes starts, or if you're writing immediate GATE exam, GATE 2022, or those people who are going to watch this video on YouTube, uh, it will be helpful to them as well. So when we start aircraft structures basics, the first thing which comes in mind is what? Basic elasticity. What comes in mind is what? Basic elasticity. Okay. So we start always with the basic elasticity, guys. Okay. Now, basic elasticity is what, if anyone knows, what is the basic elasticity? So basically, basic elasticity is a kind of approach which is used in earlier days in structural analysis. Or simply, you guys understand, in basic elasticity, we consider one assumption. Your material behave under linear elastic pattern. Okay. So that is what about basic elasticity. And first, before that, if you consider your structures, aircraft structures part, okay. So in aircraft structures, broadly, there are three subjects in your GATE exam. Three subjects, okay. My voice is breaking, is it?
Yes, sir.
Is it breaking? Okay, let me try just a moment. So we were discussing on basic elasticity part. Okay. So I was telling first in your aircraft structures. Broadly, there are three subjects. Okay. So those three subjects like first is aircraft structures basics, which is your strength of material. And then we have thin walled structure. And then we have mechanical vibration. So this is how, GATE syllabus. Now here, guys, we will be discussing today some concepts from this SOM, strength of material part, and which is going to be very important subject in your GATE studies. Usually the weightage for this SOM is like one of the highest weightage, around 10 marks, okay, in GATE aerospace. So 10% syllabus, you can say, is what? Strength of material in GATE exam. Now in SOM, one of the most important topic is what? Basic elasticity. Sometime from basic elasticity, in your GATE exam, there are 4 to 5 questions, okay, from this part itself. Okay, so there are several topics in this basic elasticity, and you guys know the basic most important topic is what? Stresses. Then we have other topic like strains, stress strain relationship, then volumetric strain, strain energy, thermal stresses, compatibility equations, and air stress function. So among these 8 topics, in the higher side, there are 4 to 5 problems, and usually 2 to 3 questions are always asked from this basic elasticity. So at least you can say it's like minimum 5 marks around the weightage for this. Okay. Now, if you look into this basic elasticity, we know from our fundamental, what is the relation between force and displacement, guys? You know, if you take a simple structural member, if you take simple structural member, it's like spring. Okay. So for spring, what is the relation between force and displacement?
F is equals to minus kx.
Minus kx.
So force is always equal to kx, right? So force is directly proportional to displacement for simple structure. But do you think always your structure is spring? It is not going to be spring. Okay, your structure will be complicated structure. So what we now see, you cannot use always this relation and solve the problem for displacement. Okay, so when you have a complicated three-dimensional structure and the loading also not simple, axial loading, like in case of spring. So what we need to do, we need to have some kind of analysis approach. So your basic elasticity is also one of the approach. Okay. So basic elasticity, yeah. So basic elasticity is also one of the approach to solve problem of structural analysis. Same way, you guys study strength of material. So strength of material is also one of the approach, to solve the problem of structural analysis. Then you will be knowing advanced method like finite element methods or numerical methods to solve the problems of structural analysis. If you are in fourth year of engineering, most probably you guys might have heard about numerical method or FEM techniques. Okay. Now guys, here when you start learning strength of material, so first idea you should have why we are studying strength of material. Can anyone tell? Why do we study strength of material? Why do we study strength of material, guys?
So to know the property of material and to select better material for our structures.
Okay, so you want to know the material properties and other thing. Okay, fine. So partially that is also correct. So usually we study strength of material for one reason. If you design, right, any system, if you design any system, it will have certain goal, right? Agree?
Yes, sir.
So we need to analyze that design for those goals, because that system will be undergoing some kind of loads, right, when it is in particular functioning. So strength of material is one of the approach, okay, to analyze that design. Okay, so what we find finally in SOM, can anyone tell in any design analysis what we find at the end as a output, or which every engineer or your chief engineer will look into?
Strength and stiffness, sir, and also its stability.
Stress and
Okay.
strain acting, internal stress and strain acting in a material, sir.
Okay, that's good. So in a simple word, have you guys heard about margins? Margins, like margin of safety or factor of safety or reserve
Yes,
factor.
sir.
So usually what engineers do for any design, what is your margin of safety, what is your factor of safety or reserve factor? So the whole and the final goal to find for every component of your design, what is your margin of safety under the given loads, or what is your factor of safety or reserve factor. Clear? So
Yes, sir.
yeah, so in a broader way, you always find margins and you publish those margins in certification. Okay, so strength of material is a classical approach. Strength of material is what a classical approach to do analysis. Okay, what is the classical approach means? if you can idealize your complicated structure in a simple axially loaded structure like bar or rod, or if you can idealize it in terms of a shaft under torsional loading, or you can idealize it as like beam. Okay, so beam will have transverse load. Okay, so in those cases we can use strength of material approach, right? Because their exact solutions are there. But if your structure is not in very complicated structure which we cannot idealize in this simple structure, then you have to use other approaches. Okay, not simply strength of material approach always. So as I mentioned, you always find margins or factor of safety and reserve factor. Now one thing I want to ask you guys, what is the relation between this factor of safety and margin of safety? Can anyone tell? What is the margin of safety?
1 minus factor of safety.
It is FOS minus 1.
Yeah.
So you like your margin of safety, MS, is always FOS minus 1, and your margin of safety should be always greater than 0 for any safe design, and your FOS should be greater than 1. Or some industry use factor of safety, some industry use it as a reserve factor. Both are one and same. Okay, reserve factor should be also greater than 1. So this is what, if you start working in industry, going to do if you are a structural analysis engineer. So what finally you will do, you'll find margin of safety or your factor of safety or reserve factor based on your available loads and these basics classical method. Okay, for the different loading, if it is a bending, you will have different formula. If you have axial loads, you will have axial stress. If you have torsional loading, you will have shear stress. Then we have the combined stresses also, like principal stress and all. Or sometimes you you guys might have heard about von Mises stress. Have you guys heard about von Mises stress? So this
No, sir.
okay. So this von Mises stress we are going to study when we study theory of failures. So most of the industry uses von Mises stress. Okay. So which is like a combination of different stresses. So we'll talk about that later. Now we'll come back to our basic elasticity part. So I gave that overall idea, why do we study strength of material. So as we know, force is directly connected to displacement for simple structure, and we know my displacements are connected with strain by strain displacement relations. So you guys might heard about your strains like normal strain epsilon x. So it can be written as dou u by dou x. Epsilon y, it can be written as what? Dou v by dou y. Epsilon z as what? Dou w by dou z. What is UVW, guys? Can anyone tell? These are my displacements fields. Okay, so this is what strain displacement relationship. Then strain will be connected with your stresses by stress strain relations. You will be knowing in a simple word Hooke's law, but Hooke's law is only applicable for uniaxial loading or one-dimensional problem. But when you talk about three-dimensional problem, so like suppose I have a three-dimensional stress system. So what will be your epsilon x? It will be sigma x by E minus nu times sigma y by E minus nu times sigma z by E. What is sigma x, sigma y?
Stress in X direction, stress in Y direction, and stress in Z direction.
Exactly. So you can see it's not simple relation, right? So this is known as constitutive relation in X direction. So this is how your stress and strain is connected, and then stresses will be connected by force using equilibrium equation. So this complete rectangle or this complete one loop we are going to complete in basic elasticity. So your basic elasticity in fact is fundamental of your numerical studies. If you use any numerical approach, the basic fundamentals comes from basic elasticity. The most widely used numerical approach in industry is what? FEM. Okay, so guys, if you are good in basic elasticity, it will help you guys a lot when you start working, or if you go for any interview in industry and want to work as a structural analyst, or if you go for any government job. This is one of the hottest topic from where the people will ask you question. Now we will start first with stress. So guys, what do you mean by stress?
Force applied per unit area.
Internal resisting force acting per unit area.
Yeah, so it is what in simple way, force per unit area, right, is what your stress. But what is pressure then, guys?
Pressure is normal force per unit area.
So stress can't be normal force per unit area. So if you see numerically, both are one and same. Both are intensity of force. Okay, either it is stress and pressure. But what is the physical difference? Numerically, both are same. So what is the physical difference between pressure and stress? Pressure is same at a point. Okay, in all the direction. You know, guys, right? This fact. If you take a point, your pressure is a scalar quantity. It is same in all the direction. But at a point, if you take stress, it will not be same in all the direction. Okay, so that's a difference between pressure and stress. Now, if you say in a simple word, if it is a direction dependent, is it vector?
Yes, sir.
No, it is not even vector. It is something called tensorial quantity. So that is what we are going to see. What it mean by tensorial quantity, guys, at a point, your stress will require three things. At this point, your stress will require three things. What those three things? One is magnitude.
Direction and plane.
Yes, magnitude, direction, and reference plane. Okay, so stress is a tensorial quantity. Okay, now usually you denote your stress by sigma. Okay, any stress is denoted by sigma. Okay, so what is the sigma? Sigma is delta P by delta A. Delta A tends to 0. What is that delta A tends to 0 means, guys? It's a point. Okay. Whenever you tends, your area tends to 0. What it mean? It mean it's a point. So at a point, your stress is what? Intensity of the force. But in simple way, your stress is nothing but it is the internal resistance provided by your structure against applied loading. So it is known also as what? Strength of the material. Okay, it is measurement of your strength of material. Okay, so you will have some material allowable, and if your stress is exceeding those material allowable, then your structure will fail. So that's about stress. Now usually there are two kind of stresses. One is what?
Normal stress and tangential stress.
So one is normal stress, and another is popularly known as shear stress. Okay, so normal stress is what? It is if you take a plane, okay, so this plane will have two components. One will be normal components of force on this. So suppose it is delta Pn, and there will be another component which will be shearing component, delta Ps. So if you find a stress, which is what? Limit delta A tends to 0, delta A tends to 0, delta Pn upon delta A, it is known as normal stress. And if you find this as the limit delta A tends to 0, delta Ps by delta A, so this is known as shear stress. Okay, and shear stress is usually denoted by what? Tau, okay, in Greek word, and this normal stress by sigma. But when you comes to basic elasticity, I will not look into this sigma or tau, which I am going to tell you guys once we discuss why your stress is a tensorial quantity. So to understand stress is a tensorial quantity, what you guys can do, if you take a arbitrary shaped body, now you can see this is an arbitrary shaped body. Now it is subjected to multiple loads P1, P2, P3 and so on, Pn. Now suppose I want at this particular point, what is my stress? So to find this stress, what you need to do? First you need to find what is the resultant force at this point. So to find this resultant force at this point, you need to draw force polygon. Okay, force polygon. And to draw force polygon, what I need to do, I need to cut this body by a plane. Okay, so in this particular case, we have cut this arbitrary shaped body by a plane NN and passing through this point O. So in this case, if you see the free body, you can see like this. This is what the free body after making cut. So you can see there is a resultant force delta P acting at point O. So you can see on the opposite side also there is a resultant force delta P, because this is in equilibrium. Now you can see this delta P is making some angle theta with this plane. So there is a normal force and there is a shearing force. Now what happens, guys? If you change this plane NN with the new plane this MN, MM, what happened? If you change this plane, this angle, the angle made by this resultant force will change from reference. Because at the particular point, this will not change. The direction of resultant force will not change because it is coming from force polygon. So what will change? This theta is going to change. This theta. So we know what is the delta Pn. What is the delta Pn, guys? It is delta P sine theta. And what is the delta Ps? Is delta P cos theta. Now, guys, if you change theta, this normal and shearing force will change. If your normal and shearing force changes, that means what, guys? Your normal and shear stress will change. So that means what? If you change your reference plane, your stresses will change. So at the one single point, you can have infinite number of plane passing through that. So we'll have infinite number of stresses. Okay, so that's why your stress require magnitude, direction as well as a reference plane. It is known as a tensorial quantity, and it is a second order tensor. Yeah, anyone has any doubt on this part? Why stress is a tensorial quantity? Anyone
So
has any?
how tensor is different from vector, sir?
Okay. See, vector means it requires what? Magnitude and direction. Okay. So you can say even vector is a first order tensor. Okay.
Yes, sir.
So first order tensor. Now, since stress is a second order tensor, so that means it requires magnitude, direction, as well as a reference plane. Even in continuum mechanics, if you study continuum mechanics, there are higher order of tensor, okay, which is not part in our GATE syllabus or in our graduation. But if you go for master's program, there is a subject called continuum mechanics, which is basically used in fracture mechanics and all. Okay, so there you will see the higher order tensorial quantities. Okay, now we have discussed about stress is a tensorial quantity. Now there is what something called normal stress. So normal stress is also direct stress, and usually, as I told, it is denoted by sigma. And we have shearing stresses, which is denoted by tau. But as I told, in basic elasticity, we do not consider it is sigma or tau. What we consider, either it has to be written as sigma ij, or it has to be written as tau ij. So this is known as notation and direction of stresses. So what I represent, guys, here, I represent the plane on which stress is acting. Okay, and what j represent? The direction in which stress is acting. Okay, now what happened, guys? If I equal to j, then what it is? If I equal to j, then it is known as what?
Normal.
Normal stress. And if I is not equal to j, then what it is known as?
Shear.
Shear stress. Okay, now guys, I am giving one example. Suppose I wrote tau xx. What it is? Is it shear stress or normal stress?
Normal stress.
Normal.
Exactly. So in your GATE exam, in one of the questions, they have written everything in terms of tau. So the tau doesn't mean it's here. What we have to see here, this suffix I and j. Now tell me, guys, what is this sigma xy? Is it normal or shear stress?
Shear.
Shear stress.
Exactly,
Shear
it
stress.
is shear stress. So keep it in mind in your GATE example, what you are going to see, I and j, not sigma and tau, which is Greek letter. Clear? So this point you guys have to keep it in mind. Now, this is about notation. The next important thing here is what? Sign convention. So when we derive certain formulas in basic elasticity, we follow particular sign convention. What is that sign convention? See, if you take this plane, if you take this plane ABCD, what is the normal to this plane, guys? Can anyone tell?
X.
X is the normal. So this is known as X plane. So if you write your stresses on this X plane, how you are going to write? You can see it is sigma. So first I is X. What is the direction? X direction. So what is your stress? Sigma XX. Now if you see this stress, it is sigma, plane is X. What is the direction? Y.
Right.
Sigma XY. Now if you see this stress, what is your sigma? What is the plane? X. What is the direction? Z. So this is sigma XZ. Now one more thing. Here you can see this is normal stress and it is going away from the section. So what it is, tensile or compressive? If I stress,
Tensile, sir.
yes, yes. So your stress is tensile since it's going away from the section. Now guys, if your tensile stress is going in positive axis direction, you can see it is a positive axis direction. So my corresponding shear stresses will also go in positive axis direction. Okay, clear? Now if you look here, this plane, which is the back side, what is normal to this, guys?
X, negative X.
Yeah, negative X. But if you take here stress, what will be your normal stress? Sigma XX.
XX.
Now tell me, is it compressive or tensile? Tensile. Why it is tensile? Because this is also going away from the section. Now in this case, this is tensile. But what should be the corresponding direction of shear stresses, guys? What should be corresponding direction of shear stresses? So if you take shear stresses, since it is going in negative axis direction, so corresponding shear stresses will also go in negative axis direction. Okay. Since your normal stress, which is tensile, going in negative axis direction, so my corresponding shear stresses will be also in negative axis direction. Okay, same way I can write on this, it will be sigma yy, so it will be sigma yx, then sigma yz. But if you take this bottom, it is what? Sigma yy. Okay, so then corresponding directions will be this and this. So this is how you have to draw your stresses using this sign convention on three-dimensional stress system. So this is discussed about sign part, and you can see. Can you guys see this?
Yes, sir.
So this is your three-dimensional stress system, and you can see where I have drawn all the stress components according to sign convention what we have discussed. So anyone has any doubt in this? Any doubt, guys?
No, sir.
No, sir.
Anyone?
No, sir.
So in our gate classes, I always take up all the things from scratch. So, you know, later on there will not be any confusion when we derive formulas or if we solve gate questions. Okay. So it is very important to be thorough with, you know, these simple basics. Now, guys, this three-dimensional stress system I can write in matrix form. Because in your gate exam, guys, always it's important to write things in a matrix form, especially stress, strain part. So now you can see you have normal stress sigma xx, then corresponding shear stresses sigma xy, sigma xz, then you have shear stress sigma yx, normal stress sigma yy, sigma yz, sigma zx, sigma zy, then sigma zz. So this is what your sigma ij matrix for a three-dimensional stress system. Clear, guys? So how many stress components you are seeing for three-dimensional stress system? How many total?
9.
9. So, and have you guys heard about shear stress complementary nature? Have you guys heard about shear stress complementary nature?
No, sir.
Okay, so I'll just say in briefly, what does that mean? Later on, when we take equilibrium equation, you will find your sigma xy will be always equal to sigma yx, and your sigma yz will be equal to sigma zy, and your sigma xz will be equal to sigma zx. So this is known as complementary nature of shear stresses. What I mean, on two perpendicular plane, on any two perpendicular plane, your shear stresses will be of same magnitude. Okay, either they will approach each other or will go away from each other, but the magnitude will be same. So this is known as complementary nature of shear. So when these shear stresses are same, so that means out of these 9, how many independents are there? How many independent stresses, guys?
3.
How many?
6.
Exactly. So number of independent stress components are 6 out of 9. Okay, so this can be a gate question here for a three-dimensional stress system. How many independent stress components are? So how many we have? 6. Okay. Fine. Now, once you know this three-dimensional stress system, I can write for two-dimensional stress system. What is my two-dimensional stress system? Suppose you take a XY plane. If you take XY plane, okay, this is what your XY plane. So how my stresses will look like? There is a normal stress here, sigma XX, sigma XX. This is sigma YY. This is sigma YY. Now you can see the corresponding shear stresses. This is in positive axis direction. So this will be also in positive axis direction. It is either tau XY or sigma XY. Then here you will have corresponding shear stresses. Clear, guys? So this is known as 2D stress system. So for 2D, if you write in matrix form, what will be sigma ij? What will be sigma ij, guys? It will be sigma xx, sigma xx, then it is sigma xy, sigma xy, and sigma y.
YY.
Okay, so this you guys remember. Now, in last class, someone was asking, can you provide some tips and tricks will be provided in class? Now, if I ask guys, find principal stress, you guys know how to find principal stresses, guys?
Sigma XX and sigma YY, the diagonal element.
Sigma. I didn't get what
Your
you
voice
said.
is breaking, sir.
Now my voice is clear. Is it clear? Am I audible?
Yes, sir.
Yes, sir.
Yes, sir.
All right. Okay. Now, guys, here what I said, you know this stress system, and someone asked find out principal stresses. You will be using some formulas and you will be finding because you might have already studied those formula. But what I do here, I will not use any formula. For this matrix, if you find eigenvalues, those eigenvalue will be your principal stresses. And you know how to find eigenvalues? It will be determinant of sigma ij minus lambda I is equal to 0. So what is those lambdas? Those lambdas are your eigenvalues and these are your principal stresses. Okay, so this is the shortcut method to find principal stresses. If you write your matrix in, if you write your stresses in matrix form. So anyway, we are going to use this method for one of the previous year's gate question. We will see in subsequent slides. Now, what is the next important part is what? Equilibrium equation. So before that, I have already written stresses in two-dimensional form, stresses on 2D body or in 2D plane. The next important part is what? Equilibrium equations. What is? There is a gate question, guys, from this concept, which is what? Your equilibrium equation. So, guys, how we derive equilibrium equation? Earlier in this case, what you say, stresses at a point. Okay, all these stresses are at a point. But if you take a body and if your element has some finite length, delta x and delta y. So what is going to happen, guys? Will these stresses will remain same on the opposite faces, guys? Will remain same or change? Can anyone? If you have a element of finite length in a body, will your stresses will be same everywhere?
No, sir.
No, exactly no. So what we can see, we can write a variation of stresses using Taylor series expansion. Using Taylor series expansion. So what I mean, suppose I have an element of length dx or delta x and dy. What we can write, suppose on this face, my normal stress is sigma xx. So from my Taylor series expansion, if I want to write what is my normal stress here, it will be what? Sigma xx plus dou by dou x sigma xx into dx. So what it is? The initial value plus the change with respect to that direction. So what is the direction? Dou by dou x. What the quantity is changing? Your stress is changing, and over what length it is changing? Dx. So this is from Taylor series expansion. Okay. Same way, my other stresses, this is sigma yy. So it is changing here on this face, it is what? Sigma yy plus dou by dou y, sigma yy into dy. Same way, these your shear stresses also vary. Now guys, whenever you take any structure, it will have what? Some weight, yes or no? Every structure,
Yes, sir.
right? So due to weight, what you see, there will be forces due to gravity. So those are known as body forces. The forces due to gravity is known as what? Body forces, guys. So in this case, we are considering your capital X and capital Y are my body forces per unit volume. Now guys, you know where body forces will be acting? At centroid. Yes or no?
Yes, sir.
Yes, sir.
Yeah. So now in this case, how many equilibrium equation we can have for this 2D case? If anyone knows about equilibrium from your engineering mechanics, how many equilibrium equation you will have?
2.
Hmm?
2.
Anyone else? Yeah, guys. How many equilibrium equations will have?
3.
3. What those 3?
X, Y, and Z, sir.
No. Where is Z?
Forces in x direction equal to 0, force in y direction equal to 0, and moment about a fixed point is equal to 0.
Exactly. So sigma fx will be 0. Sigma fy will be 0. Then moment about which axis? Can you elaborate
Z.
on that? Exactly. Sigma mz will be 0. So there will be 3 equilibrium equation for a 2D stress system. So one, forces along x direction summation 0, forces along y direction 0, and sigma mz 0. So now guys, when we start the classes, we will discuss this complete equilibrium part. Okay. And now I will just say the final solution. Okay. If you take this equilibrium, the first thing what I am going to get, if you take sigma mz 0, if you take sigma mz equal to 0, then I will get one thing which will be what? Sigma xy will be equal to sigma yx. So from moment equilibrium, you will find your shear stresses are of complementary nature. Now you have another two equilibrium, sigma fx equal to 0. So from that, I will have this equation. This is known as your equilibrium equation in x direction for 2D. What it is? It is sigma xx comma x plus sigma yx comma y plus capital X equal to 0. Comma means it is derivative form. Okay. Same way, you have another equilibrium equation which is what? Sigma yy comma y plus sigma xy comma x plus capital Y equal to 0. Okay, so guys, you have to remember these equilibrium equations. Okay, and there is a gate question also from this equilibrium equation we will solve in the subsequent next slide. So this is for 2D. These are for 2D. If you take three-dimensional system, So you'll have equation where you'll have another component which is also z component. So you can see it is sigma xx comma x plus sigma yy yx comma y plus sigma zx comma z plus x equal to 0. So these are three equilibrium equation in three direction for a 3D stress system. In a simple word, I can write it as a sigma xx comma x plus sigma yx comma sigma yx
Sir,
comma y. Yeah, one moment. Sigma zx comma z plus capital X equal to 0. Now one thing I want to tell you guys. Normal stress, when you represent, it can be represented as a sigma xx, or sometime it will be represented as sigma x. So if you see the single suffix, that means it's a normal stress in that direction. Suppose it can be written as sigma yy, or some people it write as a sigma y itself. Okay, shear has to have both I and J. Yeah, what you were saying, your doubt?
sir, X is body force in X direction, right, sir?
Exactly.
So I want to ask why we are taking a derivative of X for sigma X.
No, it is derivation, na? When you derive it, sorry, uh, just a moment. Just a moment. Yeah. So if you take from here the derivation, okay, when you derive this, from that derivation only these derivatives are coming. Okay, if you want me, I will just simply take for x direction. Okay, equilibrium in x direction. I'll take and I will demonstrate. So sigma fx, if you take, sigma fx equal to 0. So what all forces you see guys in x direction? This normal stress into area. So what is the area? Sigma xx into dy into 1, and it is going in negative x direction, so minus. Then this is the force, this stress into area will be force. So what it will be? It will be sigma xx plus dou by dou x sigma xx into dx into dy into 1. Okay, then this shear stress, it is going in this direction, so it will be negative sigma yx into dx into 1. Then this shear stress, it is going in positive axis direction, so force will be what? Sigma yx plus dou by dou y sigma yx into dy into dx into 1, because it's a 2D case. So for 2D case we take thickness as always unit. Okay, and then there is a body force, which is what? Capital X into dx into dy into 1, because it's a per unit volume, right? So force into volume,
Yes, sir.
this is equal to what? 0. So now you can see here, this term will get cancelled, this term will get cancelled. Now simplify. What equation you get? This equation. So now is it clear?
Okay, sir.
Clear,
Yes, sir.
right? So how these equations are derived? See guys, I went for my master's interview at IIT Madras. So what professor asked? Derive equilibrium equation. So what I did, I took a 3D stress system and I derived. But now tell me guys, which will be easier, to derive in 2D or 3D?
In 2D.
2D it will be easy, right? And then we can extend it to 3D. But if you follow your reference book Magzon, how many of you have heard about Magzon book, Aircraft Structures by Magzon? Some of you have heard, right? So in
Yes, sir. We
maximum,
are following this, sir.
yeah. So if you refer maximum, they have used 3D stress system, and which will make you tough to understand. So we do it in 2D and then extend it to 3D easily. Clear?
Okay, sir.
Yeah. Now come to your previous year's GATE question. So this is one of the GATE question. It's asked in previous year. So read this question. The components of stress in a body under plane stress condition in the absence of body force is given by. Your sigma xx is given as ax square, sigma yy is given as 12x square minus 6y square, and sigma xy equal to 12xy. Now they told in the absence of body force. What it means, guys? Can anyone tell? Your capital X will be
X
what?
equals to 0 and y is equals to 0.
Capital Y is also 0. So what will be your equilibrium equation in this case? It will be simple, dou by dou x, sigma xx plus dou by dou y, sigma xy equal to 0. This is what your equilibrium equation, yes or no? First equation, guys.
Yes, sir.
Now it is in derivative form, and already stresses are given as a function of x and y. We can take derivative and sum it, right? So what you see
Yes,
here,
sir.
2ax, then derivation of sigma xy with respect to y is what? 12x is equal to 0. So what is the a value we get from here, guys?
Minus 6.
Yeah, so answer is minus 6. Now tell me, was it tough question? It came for 2 marks, guys. Was it tough?
No, sir.
No, sir.
It's very easy. So have you, were you guys knowing these concepts prior to this class? Anyone was knowing equilibrium equation prior to this class?
Nah.
Yeah, that's fine. If you were not knowing, that's also fine. So what I want to tell guys, always if we know concepts, gate question is not going to be tough all the time. Okay, it is going to be easy only. So this is what one concept which we discuss. Now since time is almost 4 o'clock, I would like to discuss one more concept and one more problem, if time permits. Okay, because next session is there. So before that, I would like to know any concern or any doubt, whatever we have discussed till now, or any other query. Do you guys have?
No, sir.
All right. So let's discuss next concept. Okay, briefly. You guys, have you guys heard about stress transformation?
Yes, sir.
Okay, good. Because most of you will be studying in strength of material, stress transformation, and you guys might have used this triangular element, and you might have found what is the normal stress on that inclined plane and what is the shear stress. Am I correct?
Yes, sir.
Okay. Now, guys, basically, people know this, but they do not know clearly. What I mean by that, if you look here, what we discussed initially, you have a rectangular elements, right? We didn't use triangular element, right? When we
Yes, sir.
discuss a 2D stress system. Okay. So you know your stresses in what? In X and Y direction. Yes or no, guys?
Yes, sir.
Now suppose I rotate this element by some angle theta. So I will have another element, right? A rotated element. You guys can see like this. So there will be a stress along this direction. Suppose I am taking this as a S direction and this is T direction. My rotated coordinate is what? S and T. So this is what your sigma S. This is sigma T. Now corresponding shear stresses you will have what? Sigma ST. Okay. Now can anyone tell what will be the sigma S? What will be sigma T and what will be sigma ST? You guys have done stress transformation, right? Already. Now I am putting some question with you guys. If you take this triangular element and you find this normal stress and this is corresponding to shear stress, you know some formula, whatever it, okay? Now tell me guys, this normal stress is what? Either it is sigma S or sigma T. What is this stress, guys? Anyone? This is sigma S.
Sigma S.
Now I want to find sigma T. How you will find that? Priyansi, you know you have told this is sigma S because it's going in the S direction. And you know this angle will be theta. If this is theta, this is theta. So what about this sigma T? How you are going to find? So to find sigma T, guys, what you have to see? You have to take this triangular element, guys. Okay? Not component, Priyansi. So it will be normal to this. Okay? This plane will be normal to this. So if you take this triangular element, you will find sigma T. And you know already this angle will be theta. And these are your sigma X, sigma Y, and these are the corresponding shear. You can here also, this is sigma X, this is sigma Y, and this is the corresponding shear. So guys, you are understanding what is the sigma S and sigma T now? Is it clear? You can see these are your normal stresses on two perpendicular plane. You can see this is, you guys can see this is one plane and this is the perpendicular plane, right? So is it clear? What is
Yes,
sigma
sir.
S and sigma T and how you have to find? If you use this triangular element, you get sigma S, and if you use this another triangular element for your derivation part, you will get sigma T. So first thing, most of the people don't know what actually sigma S mean and sigma T means. Now it is clear to everyone, right? Now guys, I will not do any derivation. I can write always sigma S, sigma S, sigma T and sigma ST in a matrix form. This is a matrix form. So what is this matrix? C square S square 2CS, S square C square minus 2CS, minus CS, CS, C square minus S square, and it is multiplied by sigma XX, sigma YY, and sigma XY. Now guys, here, what is the C mean? C means cos theta, S means sin theta. Now someone say, what is the sigma S? If you want to write from that matrix, you can simply write, expand that matrix. So what is your sigma S will come, guys? It will be C square sigma X plus S square sigma Y plus 2CS sigma XY. What will be your sigma T, guys? If you write, it will be S square sigma X plus C square sigma Y minus 2CS sigma XY. Now guys, it is clear now for you guys.
Yes, sir.
Some
Yes,
of you
sir.
may know this formula, some of you know this formula, but now it should be clear when we use this formula, when we use this formula. If sigma S has to be found, we use this formula. When sigma T, we can use this formula. Now these are the trigonometrical formula. We can further simplify. Most of you will be aware of this formula, which is what? Your normal stress is sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. Clear na? If you simplify this equation, you will get this formula. Now come to last part, which is what your shear sigma st or tau. So what formula comes? If you simplify, it is minus cs sigma x plus cs sigma y plus c square minus s square into sigma xy, and we know c square minus s square is what? Cos 2 theta, right? So you can further simplify that formula, okay, and you can write it in this form. So this is what your stress transformation. Now guys, one thing I want to tell you guys here, this is your tau, right? This is tau, or it is also known as what? Sigma st. Now guys, here also there is a shear stress, sigma st. Now you guys tell me, will this and this will be same or not? Quickly guys.
Can you repeat the question, sir?
I am asking, this shear stress and this shear stress in these two different triangular elements, will this be same or different? These two will be same or different? Quickly guys. See, I find here also now on this inclined plane, what is your shear stress? On this inclined plane, what is your shear stress? Are these same or different? You see guys here what it is. Different. Priyansh, is it different? Others? Anyone quickly? No. These are same because I told already on two perpendicular plane, your shear stress is of complementary nature. So whatever this value will be same as this value. So when you do derivation also, your shear stress corresponding to sigma t and shear stress corresponding to sigma s will be 1 and same, because this plane and this plane is perpendicular to each other. Now is it clear, Priyanshi or others? Mr. Shivam, is it clear, yes or no? Why these are same? Okay, Priyanshi, if you see this rotated element, if you see rotated element, this is what your rotated element, right? This is sigma s. So corresponding shear stress is what? Sigma st. Now if you see here, what is normal stress? Sigma t on this rotated element. What is the corresponding shear stress? It will be also sigma st from complementary nature. Because this plane and this plane are perpendicular to each other. So your shear stresses follows complementary nature. Now is it clear? Okay, so in derivation also, if you find, either you take this triangular element or if you take this triangular element, when you find sigma st or your tau, your formula will come one and same. This, okay, which is what? Minus cs sigma x plus cs sigma y plus 2, it will be c square minus s square into sigma xy is what your tau, or it is also sigma st. Okay, now guys, we will take up one question quickly and then we'll wind up this session. So this is the question guys, you see. Okay, look into this question. What is given? Which one of the following object with inclined face at 45 degree subjected to given stresses are in static equilibrium? So guys, to solve this question, if you see all the four options, what you find? What is your sigma x given in all four options? It is given as 30. What is sigma yy?
40 megamax.
What is the tau xy or sigma xy in this case? What is shear stress in xy plane?
5√2 megapascal.
Is it 5? Here, is it sigma xy? What was the sigma xy when you see? Was that on xy plane or on inclined plane? Now can you tell what is the tau xy or sigma xy in this case, guys? If you see all four elements, you don't see any shear. So what is your shear stress?
0.
Exactly, it is 0. So
0.
if you take xy direction, your shear stress is 0. Okay. So this is given. Now what is asked? What is your sigma s and what is your tau st? Because they took this plane, right? So this is sigma s and this is tau st, right? This is unknown. Now guys, if you look here, this angle is 45 degree. So what will be this angle? What is this angle?
20 minus 45.
45, right? So that means this angle is also 45. Now we know from matrix. What we know from matrix, guys? What will be your sigma s? It will be c square sigma x plus s square sigma y, and third term is 0. Why third term is 0? Because your sigma xy is 0. Now what is the tau st if you find? It will be minus cs sigma x, then it is what? Plus cs sigma y. Then third term is 0. Why 0? Because you don't have in xy direction shear stress. Now guys, what is the c? It is cos 45. What is the s? Sin 45. So guys, can you find what is the sigma s and tau st value coming?
Yes, sir.
So tell me what is the
Sigma
sigma s
is
value?
equal to 35 megapascal.
35. And what is the tau st is coming?
5 megapascal.
Okay, good. Now you can see, if you see options, your sigma s should be 35. So that means what? A can't be the answer, C can't be the answer. What is the correct answer? Can be B or D. Now guys, if you see the direction of tau, it should be this, right? As per our formula, it should go in the positive t direction, right? So we got shear stress positive. So that means this is the correct. This is wrong. Clear now? Why D is wrong? Because for your formula, your shear stress direction should be in positive t direction if tau st is positive. So you can see B is the correct answer. Is this clear to everyone? Yes or no? You guys can quickly tell. I will tell you how to recheck this is correct or not. Is this clear? Yes or no, guys?
Yes, sir.
Okay.
Yes, sir.
Everyone clear? Now someone says, sir, how you have taken? Okay, or sir, how I can check whatever I have done is correctly? There is a one way. What is the way? You can take for all the elements, what you can do? You can take one thing. For all element you do sigma fx is equal to 0, sigma fy equal to 0. Only B will satisfy these two. Now guys, the given are stresses. So always when you take summation of forces, you multiply these stresses into areas. Okay, so if you know little bit of engineering mechanics, you can draw force polygon and you can check all 4 options. Only option B will satisfy equilibrium, because whatever formula we have derived, those we have derived from equilibrium only. Is it clear to everyone? Yes or no? Anyone has
Yes, sir.
any doubt in this? Okay, so this was brief, and this is how I take my classes, and these are the classes for aircraft structures basics. Naveen sir, are you there?
Yes, sir. Dinesh sir, good afternoon.
Yeah, good afternoon.
Yes.
So I have just wind up my session, sir. I'll make you presenter. Okay. So
Yes. No issue. You can just
yeah,
wind up
sure.
your-
Yeah. Thank you, sir. Thank you.